Okay, it's 9:30. Let's get started and rolling. Morning, everyone. So excited to be back today. What we're gonna do is we're gonna first make a few announcements. We're closing to finishing up the second chapter, chapter 7. So we're gonna use the next 2 to 3 classes to wrap everything up. So I'm thinking about a test on November 16th. Which is roughly
next Thursday.
No, Tuesday. What the plan is in 2 weeks from now, okay? So we're gonna use 3 classes to finish 2 to 3. Then we're gonna have a review of the homework and have some office hours to answer any questions you have regarding the polymer solution class. With that, we should be able to wrap this up. Then we got about the last chapter in rubber elasticity. So we're going to spend some time to talk about rubbery material after this. Test format will be similar. And for the other half of the homeworks, I have put out in the Canvas. So if you guys can give it to me by next Wednesday for the second round of the homeworks for this, well, that would be great. We're going to go through the class on Thursday, okay? With those logistics out of the way, so let's come back to what we have been doing in this class is polymer solutions. So what we have learned so far? Can someone help me? Especially the last lecture, what did we do? We spent a good 50 minutes together, so what we learned from the last lecture? Take a look at your notes. Go ahead.
We related the virial expansion coefficient to chi.
Yeah, that's a big part. That's probably the first 10, 15 minutes. Then later part, we also did something to talk about the phase diagram, right? So I mentioned a couple of times phase diagram is quite important, quite useful. So we discussed there's 2 things in the last lecture. There's a plot of phase behavior versus the temperature. So let me get one of such picture to remind everybody what I mean. Not here. A couple back. Okay, here is a good. So remember we plot temperature versus volume fraction. That's one way of plot it. This one we call phase diagram. Very intuitive to use. It's like a treasure map. You give an elementary kids tell, hey, here is a treasure, no treasure, or phase separate, phase mixed. It's very easy to read. You don't need any knowledge. So it's like the final guidebook. We didn't talk too much how we get to there. So in today's lecture, we're going to go into a little bit deeper, talking about how to link the other type of the diagram we talked about, which is delta G versus temperature, and link those two together, okay? So that's the other half of the phase diagram we talked about. The delta G, remember this is the delta G, this is the phi. It's not T. Although this axis is basically the same between 2 plots. So how do we go from this delta G plot to the phase diagram plot is what we're going to cover today. Okay? So at the end of the day, the ultimate goal is I tell you a chi parameter, and you can go back. This may be a stretch, but you should be able to go back to plot out what is delta G versus a phi parameter. And from that, you can take one step further. Use a single chi parameter to predict the phase diagram for your 2 components. Okay? So we talked about several criteria why some of the material was spontaneous phase separate, but the other would not. Depends on the shape of the delta G depends on phi parameter, right? So the conclusion is if your second derivative of delta Gm with respect to the phi is a positive value, this particular material will not phase separate. It will be fairly stable. if it's phase separate into two components, the total system energy will be higher than not phase separate, so this wouldn't be preferred. So your material should be stable indefinite if sitting anywhere, any composition along this line. I made this volume fraction, make this, they are going to be pretty stable, right? We also talked about Sicknick criteria, which is unstable states. In this case, this is where we start off. Once we phase separate, we're going to create two different volume fraction, and even a linear combination of these two delta G will give you phase separated delta G will be lower than where we start off. So that means we will be phase separate spontaneously. So if I prepare a 10 mg per ml of solvents, just to use a random number for example, 10 mg per ml, it will phase separate something lower concentration, 3 mg or even 1 mg, the other is more concentrated, okay? So it will like to phase separate and form two layers. And in reality, the delta G won't be that simple. So for solution, as we know, delta S will be symmetric. So this is what would be potential delta G, depending on the chi would be here, depending on what is the value of chi, depending on the strength of chi. You can see at low chi, you're always going to be favors the mixing. When it's in the bigger, then it starts to create some trouble. So let's use 2.5 for example. If I prepare this one, it won't be happy, because if I take second derivative, the middle part of the curve is concave down, so it will phase separate. But if I have something located here, it will be in good shape. It won't phase separate, both here. So this actually is a interesting case where you have regions are stable and regions are unstable. So polymer is going to be even more interesting, where your phase diagram will be asymmetric, where it will be distorted in one direction or the other. Depends on what is N1, N2, which represents degree of polymerization for two of components you're going to mix. So, okay, so today the question is, how do we get the phase diagram? We kind of qualitatively talked about their link. How do we do it quantitatively? And that's what the goal of this class is. Let's see how do we do it quantitatively, and how do we link the free energy landscape. We like to call it landscape because it's go up and down, pretty like the west part of the US, you have mountains, you have valleys. Here, we're going to do the same. So for the delta G, we can perform a couple things. First is we can perform second derivative to the phi. And if everybody recall, if we do second derivative with respect to the phi, we can know the criteria if your system will be stabilized or non-stabilized, right? So if we take it, you will see this would be a transition point. Imagine there is a delta G curve looks like this. This will be an imaginary transition point. When you take second derivative, it will be equal to 0. And you would have another one here. And this is the second derivative value, okay? So it will surpass 0. This will be always be positive. Within this region, it will be positive. And within this region, it will be negative, okay? That's what this blue curve is trying to show you. Then you surpass 2 points that the delta G second derivative will be equal to 0. What's the physical meaning of that? So that means at the left side of this curve, everything will be concave up. It will be stable. After this point, until you reach next point equal to 0, which is determined by this point, delta G equals to 0, you will reach a second point that you have start to go into the stable states, okay? So this is unstable states. Any question for this part? This defines the boundary of you has the potential to phase separate or not. The other part that is interesting is we also could consider the tangent of your delta G curve with respect to these two. These defines another important phenomenon. So when you has another phase separation going to happen, what would be the possible energy state it's reached? So this is a little bit intuitive. It's not the lowest point here. It's actually the tangent, but here it's a little bit harder to see. Okay? So let's go through this particular phase diagram and let's explain to everybody. So we have potentially an interesting phenomenon that if we have two minima, so we have seen that in the polymer system, your symmetry of the phase diagram will usually be disrupted. What that means is there will be one side will be higher with respect to the other height because of entropy effect in the Flory-Hagen theory. So assuming this will be your imaginary curve. So now let's consider a mixture of composition at the point A is stable with respect to the B and C. So that will be the point A. That will be B and C. So what the system could do is it will phase separate into B and C. Okay? Because if we look at these two are going to be the lower than what we have reached from here to there, right? Sorry, the linear combination B and C will be lower than A. It will phase separate. Correct? But is the B most stable states? Not necessary, right? So the question basically says, if I pick any 2 points on the curve, what would be the lowest possible intercept between this vertical line and this 2 lines on the curve? So if I move these 2 lines here, will intercept with this dashed line here. That means after phase separate, I potentially have after phase separate free energy to reach here. Or if I go this state, it has free energy. So if you move around all the possible combination, you're going to reach the conclusion. The lowest possible intercept between these red lines, remember the red dot has to be in here, is going to be the tangent between the lowest point to another lowest point will intercept here. Is it possible I reach the after phase separate free energy here? No, because I could not draw a line here with some imaginary line here because they don't exist. So this defines what would be after phase separation, what your composition would be. If I'm prepared, this concentration, it will phase separate into D and E. D point have a given low concentration. E will give you a slightly higher concentration. Okay? So this basically says what I already told you. D and E would represent most stable energy states. Okay? Any question?
I guess I was just going to ask, is on this graph, would
Yeah.
E, even though it's a higher concentration, has a lower free energy in the system? What?
E has a lower energy. Yeah. So the reason why you can phase separate D and E is you could not reach everything to the E. Then you change the conservation of mass, right? So assume this is 10 mg per mil. This would be roughly 15. This would be 5. You can share some of the money or share some of the polymer between these two so that you can split it into a 5 and a 15, but you cannot reach everything to 15 mg per mil. Because you can, unless you add external material in the system, which is not the case for phase separation, right? So the other part is what we want to call it equilibrium states. So this consider basically that when we have equilibrated states, what would be the total energy of system? So what we're going to do here is just to use a chemical potential as a mean to understand. Okay? So chemical potential is a parameter we can add them together using a quantitative way. What that means, you can do a linear combination if you have a certain alpha phase and a beta phase. As we can see, this is a phase separated scenario. One has dominantly solvent, the other is dominantly polymer. Okay? You can use a linear combination approach to combine what is the delta G could have. It will be N1 is a molar volume, and the mu1 is a chemical potential for the A phase. Okay? So we can get the molar change in Gibbs energy. And there is one interesting fact, N1, N2, when you add them together, they are not a quantity number. But X1 and X2, which are, X1 is a molar fraction. So X1 add to X2 has to be 1, has to be 100%, right? So using a little bit of that knowledge, we can actually construct the binodal point and spinodal point. So we kind of defined in the phase diagram what these 2 points are, right? Binodal and spinodal are 2 of the conditions. Binodal point will be represented by these 2 data points, and spinodal point will be defined by here. Anything within here is not going to be stable, but anything here will be metastable. If you recall the initial image we talked about, there was some grayish region represents right in between here. Okay, in here it will be stable states. Okay, so that defines spinodal condition is very easy. Second derivative equal to 0, which means when the point will transit from concave up to concave down, which is defined by here. And binodal point is, remember, it's not lowest point. If they're symmetric, then the tangent of these 2 curves happens to be the lowest point. Okay? If they're not straight, if you zoom in, it's actually intercept with the side slightly. It will be off. So, okay, so here is, so now we know how to define this line, spinodal, second derivative of delta G equals to 0, and we know how to define the binodal. So how do we get this diagram from the delta G? Anyone can help me? Okay, let's take a look at the last curve again. This is what we get from the delta G curve right here. As you can see, how do we link this particular curve to the next one, to this one? Not too hard. Not too hard. Why? So there's one caveat I want to mention. In the case of delta G curve, we only draw one. That particular curve is respect to a given temperature. Okay? So what happens is once we move the temperature up and down, the delta G will have a different dependence on the phi. Okay? Your curve will be looking very different. But let's assume we pick one temperature. Remember, this is the T versus phi 2. If we fix the temperature when t is fixed, we took an intercept of the horizontal line with this phase diagram. Let's have a t temperature of very high one. Remember this. Let me try to erase it. Oh, come on. It doesn't work. What should I do? Let me see if I can delete it, okay? Discard. Perfect. All right, let me take it seriously. So at high temperature, I think hopefully everybody understands what I mean by that, is you're going to have a different shape and geometry by this. At a high temperature, then now your binodal and spinodal point is going to be shifted to here and here, which is roughly the intercept binodal, and when it changes conformation, which is right here. And when you go even higher, this point might totally disappear. Look like this. This will define as you always have one phase, okay? So once we change in temperature, you're going to get different values of those for cross points. And if you go even higher, you might have one phase. That means it's always going to phase mix. You don't have a local concavidad in delta G dependence of T value. Okay? So this is how we link the delta G dependence on the temperature versus the phase diagram. So they are basically interchangeable. If you know delta G, you should be able to construct your own phase diagram. There's also a critical concentration, phi C. So this is where at the critical temperature, what will be the phi C is. That's also have some physical meaning. Here's what I mean by you can look at the second derivative to get with respect to what is critical temperature. So how do we do it? We take the first derivative already shown in the last slides. We take it once, partial derivative with phi 1. We take it twice. It will give you this particular relationship. So with respect to 1 equal to 0, we can get the critical value for the chi, okay? And chi is tied to the temperature as chi effective roughly equals to A plus B minus B divided by T. We can use that to get what is the TS. If we know what is phi S, we know what it will be the T, right? It's just one unknown. A and B are already defined. These are the constants you should be able to look up. So this is where we can define the T critical temperature. If you know what is the all the constants within respect to the chi parameter. There is also a critical concentration that we need to look at. Critical concentration is defined at what phi values you would have this particular T critical temperature. So we just need to apply chi s, take the first derivative, that will be equal to 0. Remember that was the tallest point, so chi s multiplied critical concentration at the critical temperature will be equal to 1 divided by 1 plus root square of n. So if you, let's assume your dp n is 100, root square 100 will be equal to 10. So 1 divided by 1 plus 10 roughly is 0.09. So your curve will be all shifted. Let me see. Yeah, I indeed have one. So your curve all will be shifted to the left side of it. That's a phase diagram for a polymer. Your phi c is no longer 0.5, but it will be determined by 1 divided by 1 plus root square of n. The higher the degree of formulation, the critical concentration will be more squeezed to the left side of the axis, or when phi will be phi c will be even smaller. Okay. Okay, so let's stay at this curve. I kind of explained to everybody for how we go from the delta G to a phase diagram. So if we assume there's 3 different scenarios at 3 different temperatures, so this will be the temperature 1, temperature 2, temperature 3, how this delta G shape will be different. And we already go through that. So when it is T1, we get a critical concentration with respect to A, B, D, E, what defines as spinodal and binodal, and again spinodal, binodal and spinodal, and that's the critical temperature. Okay? Any question for here? And that's again the same definition we have talked about. How to reach the B, D will be the second derivative of delta G equals to N. AC will be the lowest chemical potential energy possible when you have a binodal curve. And critical point will be equals to first derivative, second, and third, all going to be 0. Especially the third derivative will be 0 because it's a hysis. The second derivative will be defines this point, the transition point. The third defines the tolerances. And for a solution-solution mixture, it will be symmetric. In this case, it's not perfect, but if you imagine in the regular solution theory, before we talked about Flory-Hagen theory, in that scenario, you would have a perfect symmetric one. But now in the polymer mixture, it will be look slightly different, okay? And this will be roughly the phase diagram defined by these dashed line, and the solid line would define your delta G versus phi curve, okay? So that's how we translate these two plots, how to link these two. For the polymer, the overall shape will be, if it's a UCST, it will be similar, but everything will be asymmetric. Everything will be very, very squeezed to the left side of the curve. Okay, so that will be TC, critical temperature, and this is UCST, upper critical solution temperature. And these I show 3 different degree of polymerization. If you have dP goes up, your phi C will be further pushed down. Okay, so that's why this goes up. This is squeezed more and more. So this will be a real polymer phase diagram in a solvent. So Flory-Hagen theory is basically the fundamentals behind it. If we get the value delta G dependence on N1 phi 1, we can use that to look at the phase diagram. But a lot of time, your polymer might be polydispersed, and don't worry about that. The polydispersity can be accounted as well. It's just going to broaden the phase transition. Instead of one sharp one, you can imagine low molecular weight would have a transition here. High molecular weight would have a different one. It just makes the phase transition not that clear. But it doesn't change any fundamentals we're going to talk about here today. Okay? But as a polymer physicist, I always ask my chemistry friends, please make it a PDI-1. They just tell you it's impossible. Not yet, until they find a good way to do that. So, any questions so far regarding how we link the Gibbs free energy with respect to the phase diagram? Any question? This is a good time to ask. Okay. So I assume I give everybody a delta G depends on T, you can draw a phase diagram for me? Yes? Good. So, what about the limitations in what we have talked about? There's several potential limitations for the theory as well. So one of them is basically this is a Flory-Hagen theory is most applicable to the concentrated solution of polymer-polymer blends. It's not so easy to apply to very dilute one. Okay? There's one assumption that when we place molecular in the lattice, again, this would be just a lattice theory. It was assumed that probability of given neighbor site is already occupied equals to the fraction site of occupied at the present of the placing process. So that's kind of one assumption we show. But at the very low concentration, now the concentration is no longer uniform. And locally, at this region, you have a high monomer concentration. And there's a larger region where your monomer concentration is 0. For example, where my hands is pointing at is 0. But here is relatively high. So the global average, here, what we call it a global, means the average of the whole system. You can get from the total number of the red dots it occupies with overall. This is not going to be, by taking the global average, the number of possible conformation is overestimated in the very low concentrated region. Okay, so the mean field theory, which is basically taking average of everything, is not applicable necessarily here. That could introduce quite some issues. The other one is when the concentrations increases, you can have more reasonable assumption that your system averaged concentration locally is very similar to the globally. So it is no longer a problem. So how do we decide what is different concentration region? So we can look at this particular example. You actually will learn more about the average versus the snapshot concentration more in the dynamic light scattering in the next class, but I'll give you some information. So in this case, throughout the course, we currently talk about concentration is central to many topics. When we mention phi 1, we use the total number of polymer chain divided by total volume available. That gives you the polymer concentration. But in reality, that's not the case. For example, let's take a look here. This is a single chain dissolved in this vast amount of solvents. So if we look at this plot, it's plot concentration with respect to the x-axis. So we can go from left to right to look at when you start to show up a polymer chain. So when you don't know how much is in it, all you can do is use the weight divided by volume. You can get an average concentration as shown here as a C prime. That's what you perceive the concentration is. But in reality, when you look at it locally, there's heterogeneity. There's a region, you don't have any concentration, for example, these area. But when you hit the polymer, at this region, if I just cover everything else locally, this one has some fluctuation, but generally they will be much higher than what you have. In one limit, we would have melts. You would have polymer chain everywhere. So when you walk around, you have some fluctuation, but generally speaking, what you perceive the concentration will matches what you go from left to right. even in semi-dilute case, you have solvents, you would also follow the similar scenario. You would have C fluctuation over different range. That's actually the reason give you the ability to do dynamic and static light scattering, where the fluctuation of concentration gives rise to the contrast of your light to be banded at locally when there is more chains versus other. Okay. So it's good to think about different regions in the different polymer solution. When you think about you putting polymers in the solvents, you start with very dilute, and then you go up into more concentrated region, then keep going. You can keep going up until you go into no solvents, only polymer. That is effectively a melt states. So what can we learn, and how can we define a few different concentration regions? As some of the pioneers does polymer physics, when they measure solution property, they realized some of the materials property are not linearly increased with the concentration. For example, viscosity. Before, the polymer coil could touches another coil, versus after one coil is sitting next to the other, they observe totally different dependence on concentration versus with respect to viscosity with respect to concentration. Okay, so one of them is useful is define what is the overlapping concentration. Overlapping concentration defines if you perceive a polymer has a given coil size, when you increase number of them, you can see the yellow region going to start to fill it up. And when the yellow region is more or less filled, everything is in this box. Can we still feel it? Yes, you can have the polymer more closer contact with each other, or even interpenetrating with each other. So the initial contact we call it overlapping concentration. That means when you have a polymer coil start to touching the other one. Okay? Think about the classroom. If everybody can reach their hands out, and I ask if we pack as dense as possible, that's roughly the idea of overlapping concentration. But you can certainly pack more if you have to really, back to back, packed really close. You can go even higher. So in this scenario, this will be useful to understand how much polymer we have in the system and how they would overlap. We already roughly talked about this C star, which is defined as overlapping concentration when you have one coil packed with the other. How do we calculate this? You wouldn't need to pack this like I showed here to count how many coils, how many polymer. All you need is just to assume one particular coil. Okay, we basically pull this up and understand how much mass you had within this particular sphere and how much volume it occupies. So your total volume will be equals to number of polymer multiplied by unit volume of each polymer. So this is M. M is number of how many moles. V2 is how much each are. As I mentioned, we can use the density to calculate that, how much mass we have divided by how much volume per each chain, which is pretty accurate to get that. Mass we can get from N, just a mole. M is a molecular weight. And mass is equal to 4 divided by 3 pi cubic of Rg. That's the radius. That's basically defined as sphere or spherical volume. And we write the 3 in the upper portion of the structure just so that we don't need to write full source, but you got the idea. The concentration equals to mass divided by volume. And Na is just Avogadro number. That's tell you M divided by Na tells you how each individual polymer chain weight in terms of their mass. Okay? Here is some more example about overlapping concentration. We're going to apply some scaling arguments. We kind of used it in the first lecture. We talked about what scaling is when we talked about polymer chain. Scaling means we only consider their relationship. So instead of write 4 divided by 3 pi Rg cubic, we can just directly write V2 is proportional to Rg cubic because the others are constant. And we can reach a conclusion that C overlapping concentration will be equal to the mass. Mass is proportional to dP. So it will be proportional to N divided by Rg squared. We can further apply the argument of what we have showed in Gaussian chain. Rg squared will be proportional characteristic ratio NL squared divided by 6. Or we can define a p term, which is equal to C infinity characteristic ratio divided by 6 and NL squared. Once we apply everything we can get, C infinity will be inverse proportional to n power of 0.5. L is the bond length. That's fixed. We don't need to worry about that. P is also fixed. So in the theta solvents and in the good solvents, we will reach to different values in overlapping concentration with respect to what the Rg's are. So this is defined by here. So in the theta temperature, that will be defined be n power of 0.5. But in theta in good solvents, remember Rg will be proportional to NL squared, n to the power of 0.6 instead of 0.5. And this has influence because when you coil Rg is increased, the overlapping concentration will have a stronger inverse dependence on n. When we apply that value in Rg, put this thing here, you will reach here. Okay? It's missing a dash line here. But anyway, when you compare the C characteristic overlapping concentration, you will see that overlapping concentration is decreased with the coil size. In a good solvent, your polymer coil expands, so you will reach that critical concentration much earlier as compared to the case where you have a theta solvent that's slower. That impacts the viscosity, and you can actually measure what we have discussed in overlapping concentration. As I mentioned, viscosity is a good way to see when your polymer start to entangle or not. And viscosity depends on the concentration. If you plot in the data here, you will see initially it will show at very low concentration a linear increase in viscosity with respect to the concentration. So the more polymer coil you add in there, there's going to be an increase. And why the field circular dots looks very different in slope with respect to the other one is because in this scenario, we would have the polymer start to entangle. And this entanglement is dependent on the overlapping concentration. In the tangled states, the more polymer you put in there, you're going to have a different dependence on the viscosity with respect to concentration. We can look at intercept and get this C star overlapping concentration. So we can use overlapping concentration, look at, by simply compare the viscosity at the transition point. So here's an example. We can use that looking at the polystyrenes, the behavior in terms of overlapping concentration. We can, this is an example. If we know the characteristic ratio is 10, we know that PS has a molecular weight about 104. We can use that to find overlapping concentration. So this is a little bit revisit what we have seen in the previous lecture in chain conformation parts. We can get the RG, we can get the molecular weight, and we can get all the volume, and you can look at overlapping concentration. So this is not too high. If we convert to some of the number we used in our lab, this roughly is 58 milligrams per milliliter. Okay, that's about 5.8% in volume, roughly. So now actually, we need to consider the density. The real volume is 0.17%. It's even smaller. So you can easily reach overlapping concentration for a polymer with relatively high molecular weight, even at low. Okay. So with this, we also chat about one bookkeeping parameter called overlapping concentration. Defines when the polymer coils start to overlap. And any question for me at this point? Please. Yeah.
Do you take into account like what what configuration the polymer's in? Is it in a random coil or a rod? You get lower level of entanglement with the rod.
Yeah. So in this scenario, we just consider a spherical structure. We didn't consider anything strange. It's just a polymer in a good solvent, I think. Yeah, that's what we showed in a good solvents right here. That's how end-to-end distance dependent on C and C infinity and L. Okay, but I'm pretty sure when the polymer is confined, this is actually an interesting field. Depends on who you talk to. Some research field believe if you have a Gaussian coil, think about it's like a ball or sphere if you have a polymer freely moving around. But if start to have one-dimensional confinement, you have let's say you have two hard surfaces coming to squeeze in. Some researchers reported that when you compress in one dimension, it doesn't expand, doesn't follow the conventional wisdom. If you have, for example, a bread doll, when you squeeze in one dimension, it will spread in other. But in nanoscale, it didn't follow that. But there's also other discover people say it should based on other calculations. So if you're interested, I'm happy to show you a few discover people do or research done on confinement on chain conformation. There's also in the textbook of the other one we didn't use is Michael Rubinstein and Ralph Colby's textbook in quantum physics that looks like reddish color. In that book, they talked about another example of, they called it Alexander Degin brush. So if the polymer is absorbed to 1D surface, how does the polymer coil behave? If you're interested, I'm happy to share with you and explain to you their concept as well for one-dimensional absorbed polymer coil. But anyway, so the other part that I wish to cover in the next class is when you think about the phase diagram, there is importance with respect to how to get the G. And with respect to the delta G, there is a very important parameter is chi. And we kind of chatted briefly what is chi parameters are. The chi parameter would be equivalently depend, or in the layman's language that explains how repulsive interaction your two species are. So when the chi is larger than 0, there's unfavorable interaction. But how do we measure the chi and how do we get these chi values? We haven't discussed in depth. So if you go back to the Tim Rogers textbook in chapter 7, there is a small section talks about solubility parameter. So in the next lecture, we actually going to use some time to explain how do we get the how do we get the chi parameter based on some simple solubility parameter estimation? So with that, I think there's a couple minor points I will make. Then I'll try to finish this chapter in this Thursday's class. Okay. Any other question? If not, then we can finish today's lecture. But feel free to stop by my office and ask more questions.